helpful for you to have your Group 4 packet handy. Probably be helpful for me to have one handy too. So Chapter 4 packet. And I think what we'll try to do, it's been a week. I mean, we missed a day. And missing a day in an 8-week course like this is missing a lot. So we're going to try to catch up on some things today. We started Chapter 4 last Thursday. And we covered 3 topics. I'm trying to remember what those 3 were. We introduced the equation. So we introduced a chemical equation, balancing a chemical equation. And I don't know how deeply we got into mass calculations using did we do much of that? Okay, that'll probably come later today. Yeah, that'll come later today. And then we looked at the precipitation reactions, and this chart and this chart is in your packet. So you need to be conversant with the information that's on this chart and how to use it to predict whether or not there is a precipitate, to complete reactions, to write. Let's see, that's the answers. You don't get that one. You want that one? Yeah. Okay. No, this one comes at a premium. That one is free of charge. And then how to write net ionic equations. Did we get that far? Writing a net ionic equation? Okay, let's do one of those, and then we're going to jump right into a new topic. Let's just take one of these examples right here. Or let's take... This is a good slide to come in here and use that chart to predict. So let's take a look at this chart you have. And let's do 3 of these real quickly. Look at this chart. A, silver sulfate. Would you predict that that's soluble in water or insoluble in water? Silver sulfate. Insoluble? All right. I don't have the chart up there. Look at the chart. Oh, let's see. I got the chart right here. Okay, now, how do you do that? Silver sulfate. So look at sulfates right here. Sulfates. Now look, it's in column of soluble compounds. Exceptions. Silver. Okay? So most sulfates are soluble in water, but here are the ones that are not. Silver, calcium, strontium, barium, mercury, and lead. Hence, S. I didn't write that very well. Now remember, S doesn't mean soluble. S means solid. It would be a solid, not aqueous. Okay, let's take... let's see there. Sodium phosphate. What do you think about sodium phosphate? Soluble. If I looked at phosphates down here, it says most phosphates are not soluble in water. What's the exception? Alkali metal phosphates. Why? Because that agrees with the very first rule, which is that all sodium compounds are soluble in water. All right? All sodium compounds.
I think that's a bad one.
What's wrong with that one?
I don't know, it doesn't have anything.
Oh, that has most of the answers, too. How many keys do I have floating around here?
So are these supposed to have the charts on them?
Yeah, they do. They do. Right in the middle. Where's the chart? this group 4? What's going on? All right, I'll have to hunt for a group 4 somewhere. Yeah, none of those are very good. These are all
Scraps.
I don't know. This was my group 4. I'll get you one eventually. All right, now let's finish. Let's finish a reaction. Let's say I take I need a place. So let's say I take silver. Say I take silver. All right, if I take silver nitrate and I react it with sodium chromate. Okay, I want you to, say I asked you to finish that reaction. So silver nitrate, and we're going to start out here with two things that we know. Sodium chromate, CrO4, or is that CR? Yeah, CrO4. We're going to start out with two things that we know are soluble in water. How do I know that's soluble in water? All nitrates are soluble in water. How do I know this is soluble in water? All sodium compounds are soluble in water. Okay, I'm looking at something chromate, they'll know, well, all sodium compounds are soluble in water. So now let's finish it based on this chart. Now, what you're looking at here, let's say we had a container with that in it, we have a container with this in it. What do we have? We have silver ions and nitrate ions floating around in this container. We have sodium ions and chromate ions floating around in this container. Now I'm going to mix the two together. And what's going to happen? All of these ions are going to see one another. They're going to interact with one another. And the question is, are two of them going to form a precipitate? Now, all you really need to do is look at this positive ion with that negative ion, or this positive ion with that negative ion. You don't have to worry about whether sodium is going to form a precipitate with silver. They're both positive ions. And what do like charges do? Repel each other. They're going to float around in the water and get near each other, and they're going to avoid each other. They're not going to form a compound and precipitate. So all you got to do is look at this positive ion interacting with that negative ion. Now, what do you know about sodium nitrate? Is that going to be soluble in water? All sodium compounds are soluble in water. All nitrate compounds are soluble in water. So this is about as soluble as it gets. So in our final container over here, that is now got everything in it, we definitely have sodium ions floating around and nitrate ions floating around. What about silver chromate? Chromates. Insoluble. What exceptions? Sodium chromates are soluble. But notice that silver is not one of the exceptions over here. So it's saying everything else other than that is not soluble in water. So silver chromate and here is your identifier right there that you're dealing with a precipitation reaction. That's your precipitate. Okay, now you said a minute ago we did not do a net ionic equation? Okay, well let's do that right now with this one. I'm going to erase these containers. Everybody with me on that? There's a chemical reaction. Two soluble compounds mixed together to form a precipitate and another soluble compound. All right, so this is our molecular formula, or our molecular equation. Okay, let me refer to that. That's our molecular equation. At the molecular level, that describes this reaction. Now I'm going to write an ionic equation. And what I'm going to do here, this is aqueous, so I have a silver, before I do this, I'm going to balance this equation. Let's balance this equation. Getting ahead of myself. Sorry about that. All right, let's go ahead and balance this. Got two sodiums. So I'm going to need a 2 right here. Get me my 2 sodiums. That gives me 2 nitrates. I'm going to need a 2 right here to give me my 2 nitrates. That gives me 2 silvers, which I need over here. Is that balanced? Okay. So that's our molecular equation. Now I'm going to write an ionic equation, and it's going to be balanced. So a silver nitrate is going to be 2 silver ions, 2 nitrate ions. This is going to dissociate into 2 sodium ions and 1 chromate ion. I could put AQs after all of these. I'm just not going to do that in kind of the interest of time, but it's just showing that ion is floating around in water. Okay, now in the ionic equation, this is not dissociated as ions. It is this solid. So I just leave it that way. Leave your precipitate as a combined precipitate. It's not floating around as ions. This aqueous sodium nitrate is going to be that. All right. The third one is your net ionic equation. This is your just overall ionic equation, net ionic. Now ask yourself the question, what ions do you see on both sides of this equation? Which ions appear kind of the same on both sides of the equation? Sodium
Nitrate.
and nitrate. Now we call these spectator ions. So just take them out of there. We could subtract 2 sodiums from both sides this equation, and they would disappear. You got the nitrate. Nothing happens to it. It starts out as aqueous nitrate ions. It ends up as aqueous nitrate ions. It really did not get involved in this reaction. You with me? We call those spectator ions. You know, are you on the team or did you buy a ticket to watch the game? These guys bought a ticket. They just watched the game. What was the real game? Here was the real game. 2 sodium ions reacted with 1 chromate ion to form 1 Ag2CrO4 with a solid after it. So, I mean, if you want to put your aqueuses here, that is your net ionic equation. All right? Your homework asks you to do this on 3 or 4 different problems. Complete the reaction, write the molecular equation, the ionic equation, the net ionic equation. Remember to balance your molecular equation. That is going to lead to the number of each ion that's going to be represented in the ionic equation. And your net ionic equation should be balanced. You've got an Ag2CrO4, so you have 2 silver ions combining with 1 chromate ion to form that. It's your net ionic equation. Okay, we're going to shift to another topic. So that was all under precipitation reactions. How do you predict precipitates? How do you then complete a reaction and describe the whole thing all the way down to a net ionic equation? Okay, let's talk a little bit about acids and bases. These are all acids on this page right here. These are all acids. I'll tell you what, this is a little, before we get that complicated, let's just talk about acids and bases. Here are some very common acids. This is hydrochloric. This is nitric. This is sulfuric. Okay, you can kind of, you know that the SO4 minus 2 ion is the sulfate ion. H2SO4 is sulfuric acid. Nitric acid. Hydrochloric acid. There's acetic. So the acetate ion with the hydrogen gives you acetic acid. H3PO4. Want to guess the name of that? Phosphoric. So you got to take the phosphate. You got phosphoric acid. Notice hydrogens in all of these. Hydrochloric acid will dissociate into water into those ions. This is what makes water acidic, the hydrogen ion. You have high concentrations of hydrogen ion in the water, makes a low pH, drives the pH down into the acidic range. This is a strong acid. I think I need a new pen. I don't know what I need. It seems to burn out batteries every 2 days. I just changed the battery this morning. And looks like it needs another battery. Or something. I don't know what it needs. I might need a new pen. Let's try this. When I first got this, I didn't know this thing had a battery in it. I was playing around with the head on it. Okay, so this is a strong acid. Strong acid. Strong. This is a weak acid. Or acetic acid is a weak acid. Phosphoric, I think that's a strong acid.
It says weak on the chart.
Phosphoric
Mm-hmm.
has it as a weak acid. Okay. I would think it gives off that first hydrogen pretty strongly. So yeah, acetic acid is what's in vinegar. Your mouth can tolerate acetic acid. It cannot tolerate hydrochloric acid. Hydrochloric acid will burn the skin, burn the tongue, burn the lining of your esophagus. So we can't ingest hydrochloric acid. Our stomach can handle it. Our stomach can handle hydrochloric acid, but not our mouth and esophagus. So those are acids. Bases look like this. All right, so whenever you see an OH, you're talking about a base. Just doesn't have to be one OH. Aluminum hydroxide is going to be basic. Potassium hydroxide, lithium hydroxide. All right, so the hydroxide ion generally is a base. We'll mention a couple other little situations. So what do we got over here? So a bunch of those acids I just showed you, hydrochloric, nitric, and acetic, this is the same thing as this. Are monoprotic acids. They give off one proton. An H plus ion is a proton. Remember, the hydrogen atom is a proton and an electron. It loses its electron, so the H plus ion is a proton. So that's why we call them that we're protic. So monoprotic, they give off one proton. Sulfuric acid can dissociate in two stages. Your H2SO4 can give off a proton, dissociate in water to give off a proton, and the HSO4 minus ion. And that's your strong acid. In other words, it does that very readily. About 100% of it will be in this form. Some of this will go on to dissociate into another proton and a sulfate, SO4 minus 2 ion. So it can dissociate in two stages, generating 2 protons for every mole of, 2 moles of H plus ion for every mole of sulfuric acid. And phosphoric acid is a triprotic. Now here's the deal, whether this is a weak acid or a strong acid, whether what the dissociation constant would be here for this. If this, did this 100%, that'd be a strong acid, so it must be a weak acid. So loses one, H2PO4 minus 1. H2PO4 minus 1 loses another one, you get HPO4 minus 2. HPO4 minus 2 loses another proton, and you get PO4 minus 3. So monoprotic, diprotic, triprotic acids. Some common strong and weak acids. Yeah, so the hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, hydrofluoric. This is a nasty acid. Maybe here is a weak acid, but this is a dangerous acid. You get it on your skin, and it drives down to the bone. It's really hard. It has to be treated specially to neutralize this acid. So hydrofluoric, nitrous acid, phosphoric, and acetic are weak acids. What do we mean by weak and strong? Strong means this dissociates 100%. In other words, you bubble HCl. HCl is a gas. You bubble HCl into water, and it completely dissolves. It's very soluble. It dissociates 100%. So 1 mole of HCl will give you 1 mole of protons. But acetic acid only partially dissociates. So that's what makes it a weak acid. As a matter of fact, about 1% of it will dissociate, and 99% of it will stay as the molecule. 99% is undissociated. Floating around in the water, it's soluble in the water, it's floating around in the water, but as that molecule, and so it's a weak acid. All right, so an important category of reactions is the neutralization reaction, or the acid-base reaction. And here is your general description of an acid-base reaction. An acid plus a base forms a salt plus water. All right, so we could just write in a whole bunch of different acids and bases here. We'll get different salts, but we'll always get water. And there's your molecular formula, or your molecular equation. This is your ionic equation, and here's your net ionic equation. So look at what's happening in an acid-base reaction. A proton is reacting with a hydroxide ion to form a water molecule. That's your net reaction. That's your net ionic reaction. The sodium ions are spectator ions. The chloride ions are spectator ions. You got sodium chloride aqueous as your product. Scratch those out of there. There's your net ionic equation for an acid-base reaction. The acid is being neutralized by the base, and you're forming salt water, which is neutral. Sodium chloride solution is neutral. Should have a pH of about 7. So if we had nitric acid plus, let's change the base, we're going to get potassium nitrate and water. All right, so salt, that isn't the name of that compound. That's the class of compound that sodium chloride falls into. It's a salt. Chemists generally describe or define salts as compounds that result from the reaction of an acid with a base. That's what a salt is. It's what you get when you react an acid with a base. You get a salt and water. So here's your salt, potassium nitrate. Oh, well, let's just do this, just so you keep this in mind. Let's go to a diprotic acid. Sulfuric acid plus KOH is going to form potassium sulfate plus water. Now go ahead and balance that. Is it balanced? Not balanced. We got 2 potassiums. If I go too fast, I say go ahead and balance that, and then I do it. Okay, count up your hydrogens. 2. And 2 is 4. 4. You like that? Yeah, I'll do 2. All right? Did I have you doubting it?
No.
I wasn't trying to. Okay. Did you get it? Okay, you got a 2 there. There you go. Okay. So what do we want? We want a 2 here, right there. We've got 2 potassiums. So I'm going to put a 2 here to get my 2 potassiums. I've got 2 hydrogens plus 2 hydrogens. 2 KOHs is going to give me 2 hydrogens. That's 4. So I need a 2 over here. It gives me my 4 hydrogens. Yeah, I've got 1 sulfate. I've got 1 sulfate. Perfect. I've got 2 oxygens. 2 oxygens. I'm not counting those 4 because they're kind of taken care of. So I got these 2 oxygens I got to worry about, and there's 2 oxygens in those waters, and it's balanced. And what's the point of this? Well, a diprotic acid. So 1 mole of sulfuric acid is going to need 2 moles of potassium hydroxide to neutralize it. You need an OH for every hydrogen, for every proton. This is going to give off 2 protons, so you need 2 hydroxides to neutralize those 2 protons. So here's a monoprotic acid reacting with a monohydroxyl base. And so one of these reacts with one of those to produce one of those and 1 water molecule. But one of these reacts with 2 of these to produce 2 molecules of water. And it would, it would be this. That would be your net ionic equation, basically. 2 protons plus 2 hydroxides gives you 2 waters. I'm going to skip over this. I wouldn't worry too much about the basic one. Here is it in words. Some of these slides that I just skip over, you could come back and just kind of work with hydrobromic acid plus barium hydroxide. You got it in words. Bromide, bromic, has a -1 charge. Hydrogen has a +1 charge. So it's going to be HBr. What's the formula for barium hydroxide? Hydroxide has what charge? Negative 1. Barium has what charge? Plus 2. So we're going to bring the 2 down here. So this is just the opposite of the sulfuric acid reacting with KOH. We now have a monoprotic acid reacting with a base that has 2 hydroxides. So we're going to get barium bromide plus water. Yeah, and I mean, what you can see here, you got a proton, you got a hydroxide. Each one of these is going to need one of these. So 2 HBRs are going to react with 1 barium hydroxide to form 2 molecules of water. Okay? Yes? Am I going too fast? Daniel? All right? Now look at here. Look at this. Sulfuric acid plus barium hydroxide is going to form barium sulfate plus water. There's a diprotic acid reacting with a base that has 2 hydroxides in it. Here's the right formula for barium sulfate, but 2 protons with 2 hydroxides is going to form how much water? 2. 2 waters. And it's balanced. So one of these reacts with one of those to form 2 molecules of water. And you would have this battery ran out already. What is going on? I must have really cheap batteries or some kind of a massive short in here or something. Or it's falling apart. I hate to have to do mechanical work. Oh well. Can I write on here with my finger? Not that I know of. Oh well. All right, new topic. So that was acids and bases. Acid-base reaction, net ionic equation for an acid-base reaction. This is a good slide to copy, and just like that's a good chart to have, you may want to print this off as a single slide and have it to refer to. We're now shifting in away from acid-base reactions into oxidation-reduction reactions. But before we can really understand oxidation-reduction reactions, we need to understand oxidation number. And how would we assign oxidation numbers? How would we assign oxidation numbers to different things in a chemical equation? All right, and these are the rules for oxidation numbers. First of all, rule number 1. Could this be a little bigger? Yeah, rule number 1. Free elements. So anything that shows up in a chemical equation as in its elemental form is going to have an oxidation number of 0. Oxygen, O2. That's the form it's in, as an element. Oxidation number would be 0. N2. Nitrogen is N2. Hydrogen is H2. Whenever you're just seeing a standalone element, its oxidation number is 0. Okay, these are the first couple rules are probably the easiest ones to remember. Number 2, all those charges that you learned to put compounds together, like aluminum oxide, what's the charge on that aluminum? +3. That's its oxidation number. The oxygen is -2. That's its oxidation number. So whatever charge it would have in an ionic compound would be its oxidation number. Number 3, oxygen. Oxygen itself, typically -2. When we were learning formulas, I said, okay, oxygen and sulfur, 99% of the time are going to have a -2 charge on them in a compound, like potassium oxide or, calcium oxide. It's got a -2 charge. There's okay, so hydrogen peroxide has a -1. The O2 -2 is, or it's -1. So hydrogen peroxide is not your -2 oxygen ion. That's an exception. Oxygen is usually always going to be -2, unless you see something weird like hydrogen peroxide. You can tell that's weird because, that's normally what you have is water. That's got a -2. Each one of those has a +1. Hydrogen peroxide, this is still +1s. So this O2, this whole O2 thing has a -2, or the oxygen has a -1 on it, each of the oxygens. Hydrogen, typically +1, unless it's a hydride. Unless it's bonded to a metal, like potassium hydride, then it has a -1 charge. Group 1A elements is +1. That's what you learned from when we were doing compounds putting together. Group 2A, +2. 7A, -1. Fluorine is always -1. Number 6, the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or the ion. Number 6. So let's look at number 6 for a second. So let's take SO2. All right, we haven't said a word about sulfur. So what you're going to do is go off of the oxygen. Oxygen ions have, or oxygen has a -2 oxidation number. There are 2 of them, so there's a total of -4 here. Let me erase that for a second. So 2 times -2, we've got a total -4 being contributed by the oxygens. So what does the sulfur have to be for that to be neutral? +4. So that's how we would figure out sulfur's oxidation number. We would go from the stuff we know to the unknown in the situation. So SO2, the sulfur has got a +4 oxidation number. And we're talking about the individual atom. So the individual oxygen has a -2, the individual sulfur. So what is it in SO3? What's the oxidation number of SO3?
Sulfur 6.
So that has to be a +6. So SO2, the sulfur is a +4 oxidation state. SO3, the sulfur is a +6 oxidation state. Okay, now let's look at this. Here's the sulfate ion. Now the charges of the negatives and the positives have to equal that. It's got a -2 charge. Oxygens are -2. 4 times -2 is -8. So X plus -8 equals -2. All right? So whatever the charge is on that sulfur plus the total negative of the oxygens has to equal the charge on the ion. So X equals 6 plus 6. Because that is here's what this says here. The sum of the oxidation numbers of all the atoms in an ion is equal to the charge on the ion. All right? So if the ion has a charge, then the total oxidation numbers have to add up to the charge of that ion. So that sulfur is a +6 sulfur. Okay? So that's how this works. And what's the last one? Oxidation numbers do not have to be integers. The superoxide ion, don't worry about number 7. I don't know where number 7 ever comes up in anything we're going to do here. But the superoxide ion has got a -½ charge. It's the O2 -1 charge. So you got 2 oxygens with an electron. One electron being attracted to 2 oxygens. Yeah.
Would you be able to do B on column 24?
Well, let me see if problem 24. Is this in this category here? Yeah, and this is kind of what I would like to do today. I'd like to, because we're going to be introducing so many different topics, is kind of go over one and then do a couple problems in here. What are you saying, 24 what? B?
Yes, B is in boy.
24B. Copper sulfate. All right, so what do we know about copper sulfate? We've got a positive ion over here, and we have a negative ion over here. We've got the sulfate ion. Yeah, so this whole thing has a -2 charge on it. So what does that say the charge on the copper has to be? +2. Right there. But now it does want you to give the copper, the sulfur, and the oxygen. So, all right, we've kind of figured out the copper. We'll get that. We just did sulfate ion. This oxygen is a -2. This is X. We don't know what that is. So X plus -2 must equal that. All right? So we just kind of figured that one out. Sulfur is a +6 and copper is a +2. Yes? Now let's just check one other thing out. This is the sulfate ion with a -2 charge on it, but copper sulfate has no charge. So copper is +2 +6 plus a +6. That's what this is. no charge on copper sulfate. So we got 2 plus 6 is 8, plus minus 8 is neutral. All right, so that's a way of double checking the whole thing. Do I have the right oxidation numbers for each of the elements? Well, does it combine to give me no charge on the compound? No, that's good, Monica. We want to get dragged back to this Group 4 packet, at least for one problem on each new concept, so that we see how to do some of these things. A moment ago, we were doing net ionic equations. Well, we won't worry about that right now. So we're on to oxidation and reduction. All right, so this is like problem 24 and 25, assigning oxidation numbers to compounds. Why do we want to learn how to do this? Well, when you're looking at a chemical reaction, okay, we're going to start talking about oxidation reduction reactions. And what's happening in an oxidation and reduction reaction? Well, something's getting oxidized, something's getting reduced. Their oxidation numbers are going to change. We've looked at a bunch of reactions already where none of the oxidation numbers ever change. Precipitation reactions, acid-base reactions, oxidation numbers aren't really changing. If we went back to some of these, if we went back to some of these, we didn't talk about oxidation reduction. This has a -2 charge on it. This has a -2 charge on it. The barium is a +2 ion. The barium is a +2 ion. Charges didn't change. There is not oxidation and reduction going on in this acid-base reaction. All right? You may say, well, I don't get that yet. Well, you will when we start seeing oxidation reduction reactions. All right. Let's take that N2O going to nitrogen and oxygen. N2O is decomposing into nitrogen and oxygen. And so we have 2 of these producing 2 of those and 1 of those. Okay, what's the oxidation number of the nitrogen, the N2? 0, because that is its elemental form. The O2? 0. I'll tell you how I'm going to do this. I'm going to put the oxygen up here, the N2 down there. So in N2O, what is the oxygen's oxidation number? -2. Remember the rule. So you need to go back to that chart and just know that rule number 3 here says the oxidation number of oxygen is usually -2. So we're right here. It's got a -2. So what is the nitrogen? No, the N2 in N2O. It's not elemental nitrogen. It's now been combined with oxygen. So it's +1. The 2 of them need to be +2. So I'm going to put the oxygen up here. So -2 is going up. It's going up from -2 to 0. The nitrogen, the two nitrogens is going to be plus 2, so each one is a plus 1. 2 times plus 1 plus negative 2 equals 0. So the nitrogen atoms are plus 1. They're going down. The nitrogens are going down in oxidation number. Okay, that's reduction. If you go on a diet and you start losing weight, you're reducing, right? That's reduction. The oxidation number is decreasing. Negative 2 to 0, that's oxidation. The oxidation number for that element is going up. So it's being oxidized. All right, now what is oxidation and reduction? Anybody ever heard that acronym? This is a good Texas acronym. Yeah, and what's it stand for? Okay, oxidation is loss. Loss of what? Electrons. Loss of electrons. Reduction is gain of electrons. Okay, that should make sense. Because what is an electron? It's negatively charged. So if you gain it, if you gain a negatively charged particle, it lowers your oxidation number. Your oxidation number goes down. So remember oil rig. Oxidation is the loss of electrons, and reduction is the gain of electrons. All right, let me take another equation that is a little, what's a better one to look at? This one. Nickel plus lead nitrate yields lead and nickel nitrate. Let's see what's happening there. Excuse me. Okay, nickel, elemental nickel. So we have nickel plus lead nitrate forming lead plus, okay. Nickel plus lead nitrate. Now is that, yeah, that's got two nitrates here. Forms lead plus nickel nitrate. All right. So here's our challenge. We want to figure out what's being oxidized and what is being reduced in this equation. Number one, I can take a look at this. You should get to the point where you can look at an equation like this and you say, that's an oxidation reduction equation. How could you figure that out real quickly? Well, you know that that's 0. You know that that's 0. But it doesn't start out as 0. It starts out as a plus 2. And it goes down to 0. The nickel starts out as a 0 and goes up to a plus 2. Okay, whenever you see something that has changed its oxidation number, it's an oxidation reduction reaction. It may fit into another category. There may be another name that also applies to it. But something is being oxidized and something is being reduced. The other thing you should always see is whenever something is being oxidized, something has to be also reduced. All right? You never have oxidation happening all by itself. All right, now let's take a look at the nickel. We start out with nickel. We produce a nickel +2 ion. How did it become a +2 ion? What happened to the nickel atoms to become +2 ions? Okay, it oxidized. The oxidation number went up. But why did it go up? What did oxidation is the loss of electrons. It lost electrons. How many electrons did it lose? 2. It had to lose 2 electrons to go from 0 to +2. It lost 2 electrons. Were you with me? This is the oxidation half reaction. All right? That's the half. That's half of the reaction. It's the oxidation half of it. Now the lead started out as a +2 ion, and it became lead, elemental lead. So this started out as a +2 ion. How did that +2 ion become 0? It gained electrons. Reduction, it reduced. It went from a +2 down to a 0. And it did that by gaining 2 electrons. Okay, so this is your reduction half reaction. So these 2 electrons that nickel lost are the 2 electrons that the lead gained. We never have a situation where electrons are just flying off into space. They're going somewhere for a reason. The nickel is giving up those electrons because the lead is drawing those electrons to it. And you have this oxidation reduction system. Now the battery in your car is an oxidation reduction system. And basically what they do with the battery, what they're doing in the battery in your car is inside there's a compartment where you have, let's say, it is lead. It's lead, I don't know what it is, lead sulfate or something like that. Well, let's say it was a nickel lead battery. We can make a nickel lead battery. And here's your one post, and here's your other post to your battery. So in another compartment you have nickel, you got some kind of, you have nickel plates, you have lead in here, but you have lead sulfate, or what are we dealing with in our equation? Lead nitrate. We have lead nitrate floating around in here. So we have lead ions, we have nickel plates down in here, elemental nickel, and we have, what do we have? We have an electrical circuit. And in here is your starter. And in here is your ignition switch. So it's just sitting there. It's got the potential for electrons to flow from here, from this compartment in your battery, to here, to the other compartment of the battery that wants those electrons. The nickel, the lead is more reactive than the nickel, or the nickel is more reactive than the lead, so the lead is going to give up those electrons to the lead. And it's sitting there. You put the key in the car, you close this circuit, and the electrons flow and spins your starter. This is what's happening with any battery. So any battery is an oxidation reduction system. It's basically sitting there with the potential for the flow of electrons as those electrons want to go from one reactant to the other in an oxidation reduction reaction. So is this big stuff? Oh, man. Go talk to Elon Musk, okay? What's he doing? Tesla. I don't know where's he building this factory to make batteries? Arizona, I think? Or building a huge factory. When it's done, and I don't know when it's going to be done, it will be able to supply, I think, 2 or 3 times the number of batteries that the world is currently making. It's going to pump out batteries, folks. Anybody following Elon Musk? Tesla?
The factory's gonna be all solar too, so it's actually gonna generate more power than it uses. But
Is that right?
yeah, you can use it
Okay.
to store
All right.
that energy too.
That's great. Elon Musk, well, they got the Tesla car. They're going to come out with an electric car in July that is going to be, or August, somewhere here in the next few weeks. They're going to be promoting an electric car for kind of a family car. Right now, the Tesla 3 is about a $75,000 car, but I think they're going to come out with a model that is starting to get down into the average person's price range. They're proposing batteries that you would run your house off of that battery. You would have solar cells on your ceiling that are recharging that battery, and then in the evening you're powering your house off the battery. So Elon Musk is shooting for electricity to run a lot of things. But this is what the battery does. Okay, now anybody have a problem in here that either we can do or at least talk about how you would do it? Okay, problem 27. Okay, this is what these problems are all about. Identifying what is being oxidized and writing the oxidation half reaction. What is being reduced and writing the reduction half reaction. Which one of those do you want to do? I'll take requests. B? (27B). We have chlorine reacting with sodium bromide to form bromine and sodium chloride. Okay, now if you see the way I like to try to do these, my chlorine is in its elemental form, so its oxidation number is 0. I come over here to sodium chloride, and it's in an ionic compound, and its oxidation number is going to be the charge on that ion in that ionic compound. And so I write those on one level so I can see that my chlorine is going from a 0 to a -1. And my bromine is going from a -1. How do I know that? Well, the sodium here is a +1, and the bromine is -1, and it's going to 0. So one of them, the number is going down, bromine. Oh, wait a minute here. No, the number, bromine's going up. I'm sorry. -1 to 0 is up, all right? Got to keep track of up and down, left and right, up and down. So the bromine is going up from -1 to 0, and the chlorine is going down from 0 to -1. So this is reduction, and this is oxidation. Yes? Now, I got to balance it. What do I need? I need a 2 right here. So let's write the oxidation half reaction first. We have 2 bromides two electrons plus 2 bromides is forming 1 bromine Br2 molecule. And that is gaining electrons, so that's your oxidation. And chlorine, 1Cl2, bromine, -1. Yeah, it is losing electrons. You're right. I'm sorry. That is oxidation. The bromide ion is giving up its electron. Each bromide ion is giving up an electron to form a bromine element, atom, neutral atom. Right. That's oxidation. Oxidation is the loss of electrons. Chlorine is gaining the electrons. So it starts out with a 0 charge, and each chloride ion, each chlorine atom gains an electron and becomes a chloride ion, and it reduces. So that's reduction. And if you work off of a balanced equation, you should always see that the number of electrons being lost is equal to the number of electrons being gained. We don't have an extra electron left over or something like that. With a balanced oxidation reduction reaction, the electrons should balance. And that is exactly why we don't write the electrons in the overall equation. They are, in one case they're being lost, in another case they're being gained, they're accounted for. Every single electron is adequately accounted for. Okay, let's take a 5-minute break. You might want to go ahead and do 27A and C. Take a little break.
So just a double question as far as like those electrons, why specifically is it 2? Is it always 2? Or
Well, let's just write it like this. Let's just take one of those to form one of those.
right?
All right.
That's your big uses 2.
Each one of these is a bromide ion like that. It has 8 electrons, and it's going to end up as a bromine atom like that plus an electron.
Gotcha.
All right, it's going to lose an electron to go back to being neutral. 2 of these is going to form that. And
Just 2 of those. Okay.
okay?
Makes sense.
Each one's going to give up an electron. Yeah, no, you have to get it worked out in your mind there. Okay, I want to shift over now to a really main topic, a key topic. Let me say that. We're going to go back to the chemical equation and start dealing with calculations based on a balanced chemical equation. And maybe I should make a little list. I'm gonna do a number of problems here that are just gonna be, they're gonna be representative of the different types of problems you are gonna face around a chemical equation, particularly when it comes to calculations. A lot of these things have been on how to write this equation, how to identify a particular type of reaction, but now we're going to get into the nitty-gritty of mass relationships, mass calculations based on a chemical equation. I'm going to go back to the equation I introduced you to, aluminum, pretending we're back at Alcoa. We're going to get back to Alcoa here. And get back, and I'll write some of them on the board, the kind of problem, and then I'll do it on here. But if you remember our key equation, aluminum oxide plus carbon yields aluminum plus carbon dioxide, and we balance this way. And remember, this means that 2 moles of aluminum oxide will react with 3 moles of carbon to produce 4 moles of aluminum and 3 moles of carbon dioxide. Did we get that far? We introduced this equation. We talked about how to balance it. And this sort of thing right here. Well, let's go ahead and get the molar masses. Let's just write the molar mass of each one of these reactants and products above it, so that when we need these in our calculations. Now this one's easy. It comes right off the periodic table. This one is easy. It comes right off the periodic table. 26.98, is that right? Yeah. All right. So someone get me aluminum oxide, someone else get CO2. What are the molar masses of these? Mass of aluminum oxide. 2 aluminums and 3 oxygens. Two aluminums and 3 oxygens. No, don't worry about the coefficient. Remember, molar mass is grams per 1 mole. So it's irrespective of the coefficient. 101.93. And carbon dioxide, 2 oxygens is 32. And at 12.01 is going to be 44. All right, there's our molar masses. All right, so going into today's discussion, you already have 3 critical skills. You know what the molar mass is and how to calculate molar masses. You should know by now, and that was, I think, the first part of the Group 4 work, how to convert number of moles into grams, right? You've already had some problems like that. And how to convert number of grams into moles. How to go back forth between moles and grams. So I'm not going to review that right now, but those are three key skills that you're taking into what we're going to do right now. So let's take, these are problem types. So type number 1. And this is going to be going from moles to moles. This is the simplest type of problem. Going from the moles of one thing in this balanced chemical equation to determine the moles of something else. Now, these coefficients are telling you the mole relationships of any one item in this chemical equation to any other item. So, for example, we know that you get 4 moles of aluminum for every 2 moles of aluminum oxide that react. That's what those coefficients are telling us. There's a 4-to-2 ratio, 4-to-2 relationship between aluminum and aluminum oxide. So in this first problem type, we have 12.9 moles of aluminum oxide, and we want to know how many moles of aluminum that could produce. So dimensional analysis tells me that I want to put my moles of aluminum oxide down here and my moles of aluminum up here. And what is that ratio? 4-to-2 ratio. All right? And so 12.9 moles of aluminum oxide can produce how many moles? 25.8 moles of aluminum. Okay, we're just going from, we're just relating moles of one thing to moles of another thing. And we could have any number of moles of, we could determine how many moles of carbon. We could determine how many moles of carbon dioxide would be produced from 12.9 moles of aluminum oxide. You could do the same thing there. 12.9 moles of aluminum oxide is going to produce how many moles of carbon dioxide? If you were in the environmental department at Alcoa, this might be a question you have to answer because the EPA wants to know how much carbon dioxide you're producing. Well, you're going to get 3 moles of carbon dioxide for every 2 moles of aluminum oxide that react. So 3-to-2. So how many moles of CO2 would that get you? What? 19.35 or 19.4? Yeah. 19.4 moles of CO2. Okay? So you can relate any 2 things in that equation based on these coefficients. Okay, problem type 2. Here's where we want to go from moles to grams. Moles of something to grams of something else. with our aluminum oxide, 12.9 moles of aluminum oxide. If you were in the purchasing department, production wants to make a certain amount of aluminum. They know how much aluminum oxide they're going to put in the reactor. Okay, now the question comes, how much carbon do we need? How much carbon do we need to buy to do this reaction? So we want to start with 12.9 moles of aluminum oxide, and we want to get to grams of carbon. Okay, now there's going to be a strategy here. Here's the strategy. We're going to go from moles of aluminum oxide to moles of carbon to grams of carbon. That's the path we're going to go through. Because the equation here, the equation is not a gram to gram ratio, it's a mole to mole ratio. Telling us the relationship mole to mole. So I got 12.9 moles of aluminum oxide. I need 3 moles of carbon for every 2 moles of aluminum oxide. So that converts, that gets me here. That converts my moles of aluminum oxide into moles of carbon. And then it is 12.01 grams of carbon per mole of carbon. And if you'll notice, when I do my problems, I would recommend you do that too. I don't just say 12.9 moles. Moles of what? Because I need to know where I'm at. Cross out moles of aluminum oxide. I know now that I am at the moles of carbon stage. Then I multiply by the molar mass of carbon, and I can calculate the grams of carbon. So what do I need? 232 grams of carbon? Is that right? 232 grams of carbon. Now we're coming into the real world here. Alcoa doesn't sell aluminum by the mole. I just can't imagine an aluminum company, advertising it's $325 per mole. Most customers would say, I don't know what that means. All right? I'm buying it by the pound, the ton, the metric ton. They're buying and selling these commodities on a mass basis, weight basis. So now we're starting to get into the real world here, where and say, okay, I need 232 grams of carbon to react with 12.9 moles of aluminum. Okay, now the third type here is let's go from grams of one substance to grams of another substance, and this is where you start seeing the use of this word, stoichiometry. We're talking about mass calculations based on a balanced chemical equation, stoichiometry. So whenever you hear that term coming up, that's what we're talking about. Stoichiometric calculations, we're going through mass calculations. So let's say this. How many grams of aluminum can be produced from 633 grams of aluminum oxide? All right, now the strategy this time, very similar to that. We're starting with grams of aluminum. And we're going to convert that into moles of aluminum. And then we're going to convert that, I'm sorry, back up here. We're starting with grams of aluminum oxide. We're going to convert that into moles of aluminum oxide. We're going to convert that into moles of aluminum. And then finally convert that into grams of aluminum. Let's get this. There's our equation. And we have 633 grams of aluminum. We want to know how many grams, 633 grams of aluminum oxide. I haven't had my lunch yet. My batteries are running down. So 633 grams of aluminum oxide, we're going to convert that into grams of aluminum. And what are we going to do? We're going to convert this into moles of aluminum oxide. We're going to convert that into moles of aluminum. And then finally, we're going to convert that into grams of aluminum. All right? So remember, this was 101.93 grams. And this is 26.98 grams per mole. So 633 grams of aluminum oxide. And we want to get over here to grams of aluminum. And it's 1 mole of aluminum oxide has a mass that gets me to moles of aluminum oxide. There are 4 moles of aluminum for every 2 moles of aluminum oxide. And now I know I'm getting the correct coefficient into that expression. And now it is 26.98 grams of aluminum for every 1 mole of aluminum. I've got my unit over here is grams of aluminum, my unit over here is grams of aluminum. Got an equal sign here, so whatever's over here must equal over there. Number and unit. What's the number over here? It's that mathematical calculation. That's the other part of the equation. I think I did something wrong. That doesn't seem right. So that's about 6 moles times 2 is 12. Yeah, I got the wrong number. What do you got?
Oh, I got 335.
335?
Right.
Okay, I was off by a factor of 10 for some reason. 335 grams. Somebody agree with that? Okay.
Yeah,
Did you get another number?
I got 335.
Okay.
I got 335.
All right. can't write again. I can't believe this. I gotta get myself a new pen. $335 grams of aluminum. Okay. Okay, you could go from grams of anything to grams of anything else. I mean, you could determine how many grams of carbon dioxide you would produce, it would result from this reacting. Now there's an assumption here. The assumption is that there is enough carbon to react with that aluminum oxide. And so a lot of times what you'll see is that this is your excess reactant. In other words, we're saying we got plenty of carbon. Don't feel like carbon is going to hold this reaction back or keep it from going to completion. Now you can see this word right here. How many grams of aluminum can be produced? So on number 3 here, we are talking about theoretical yield. Theoretical yield. In other words, if everything went perfectly, if you were able to completely react at 633 grams of aluminum oxide and you were able to recover every last little pinch of aluminum, then you could get 335 grams of aluminum from that reaction. That would be a 100% yield. Be a perfect conversion of the aluminum oxide into aluminum. Do you think Alcoa does that on a day-to-day basis, that they perfectly convert their aluminum oxide into aluminum? No. And no matter what reaction, the yield is always less than 100%. This is theory. You always get less than that. Even Alcoa, they fill up a kettle with aluminum oxide and carbon and heat it up real hot, and a little bit of this doesn't get reacted. They get down to the very last end of the reaction and there's no carbon right where the aluminum oxide is, even though they put enough carbon in there. They pour the aluminum out into trays to cool down, to solidify, and they don't get it all out of the kettle. So at the end of the day, they measure the aluminum they got, and it's always less than what you would have predicted based on the theoretical yield. Follow me? So this is theoretical yield. So if this stops writing, oh, this is writing again. I don't know. So let's say, for example, so this is our theoretical yield. This is really starting to bother me. So our theoretical yield is 335 grams. Now let's go on into talking about actual yield. Let's say we did this and Alcoa recovers 305 grams of aluminum from that reaction. And we want to know what their percent yield is. Percent yield equals actual divided by theoretical times 100%. Not going to get much easier than this in terms of kinds of calculation. Now, in order to calculate a percent yield, you need to calculate the theoretical, and you need to be given what the actual yield was. What was the actual yield? So they got 305 grams when it would have been theoretically possible to get 335 grams. So what is that percent yield? so they got 91% of what was possible. All right? All right, so we've covered a lot of ground. You could be asked questions that go from moles of one thing to moles of another, from moles of one thing to grams of another. Most often is this. This is the most often kind of problem where you really are starting with a mass of one thing and you're converting it into a mass of another. All right, let me go on to, I don't know if this is the last concept. Oh. Yeah, so here's theoretical yield calculations. What is the mass of zinc chloride formed if 128.2 grams of zinc reacts with excess hydrochloric acid? All right, here's where you're seeing this term come up, excess. So, and you don't, not even being given an equation. Zinc plus HCl. So we got zinc plus HCl. What is the mass of zinc chloride? So it's telling you what one of the products is. Actually, this reacts with that to form hydrogen gas. All right? So there's a theoretical yield problem. And you're seeing this terminology. You've got excess HCl. I mean, if they theoretically, or not, I shouldn't say theoretically, but if they hadn't mentioned this, you might say, well, I don't know how much you're going to produce. I don't know if you have enough HCl to react with 128.2 grams of zinc. But they're saying, yes, you do. You have more than enough HCl. All right, so we won't go through that one, but these are the kinds of examples you have here. Theoretical yield calculation. How many grams of phosphorus are needed to produce 290 grams of tetraphosphorus DAC oxide? So you'd have to write an equation there. Theoretical yield calculation. Iron oxide can be formed when iron reacts with oxygen. Calculate the mass of iron 3 oxide formed when 26.25 grams of iron react. I actually have a worksheet here that have these kinds of problems. Now, maybe not that problem. Might actually have that problem. Has something similar. All right, so we'll I'm just showing you here. They're just reaction after reaction that you could go from the mass of one thing to the mass of another. All right, here's the equation for percent yield. And finally, limiting reagents. All right, this is your toughest problem. And we're going to work through one of these. I want everybody to have their calculators. What do we mean by limiting reagent problem? This will be on the next exam. This will be on the final exam. Limiting reagent. You can think of this as limiting reactant. Let me give you a real practical example. Your automobile. Your automobile runs off of a chemical reaction. Gasoline combined with oxygen to form CO2 and water and energy. If you see a car pulled off on the side of the road, did it run out of gasoline or did it run out of air? Not air. Didn't run out of air. But that's one of the reactants. Here's your gasoline. it's reacting with oxygen in the air. It's reacting with oxygen in the air to form carbon dioxide, water, and energy. So when a car stops running because it ran out of something, what does it run out of? Gasoline. So I ran out of gas. Ran out of gas today. Did you run out of air? No, I didn't run out of air. I was still breathing. But my car wasn't running. So your car, this is your limiting reagent or your limiting reactant. Your car will run as long as it has gasoline. But when it runs out of gasoline, it still has plenty of air, but the reaction stops, right? When you run out of the limiting reagent, the reaction stops. Doesn't proceed any further. So your limiting reagent determines what your theoretical yield is going to be. Okay? This is in excess. You've got plenty of air. Your limiting reagent limits the product that will be formed. This is why we're calling the limiting reagent or limiting reactant. Okay, now let's see if I can find a good, there's one in here, but all right, here's a little diagram kind of taking my gasoline example and bringing it into the kitchen. Okay, here's your recipe for cheese sandwiches. 2 pieces of bread, 1 piece of cheese. Okay? You're provided with 28 slices of bread and 11 slices of cheese. And the question is, how many cheese sandwiches can you make? What's your limiting? 22. Okay? So what, you're saying you got, not 22, 11, right? You can make 11 sandwiches. Every sandwich has to have a slice of cheese in it. So you can make 11 sandwiches. How many slices of bread will that use? 22. You got 28. So which one is the limiting reagent? The cheese. You have plenty of bread. This is your excess reagent. This is your limiting reagent. You run out of cheese, you can't make any more sandwiches. Even though you got 6 pieces of bread left. Sorry, there's only 11 sandwiches. You follow me? So this is what we're going to have to do on a limiting reagent problem. We're going to have to figure out which one of the reagents, when we're given, I got this many grams of A and this many grams of B, which one is going to run out first? That's going to be your limiting reagent. And the other one is going to have, there's going to be some leftover. It's going to be leftover of the other reagent. Okay, now this isn't extremely helpful. It says determine which of these is the limiting reagent. Okay, this is what we have to figure out how to do right now. How do we determine which one is the limit? So let's look at this. Okay, we're doing aluminum oxide reacting with carbon to produce carbon dioxide and metal. So let's get back to our favorite little equation here. I wish I could write again on here. 270 grams and 74 grams of carbon. Looks like I might be able to write. Nope. Okay. Let's do it on the board. So we have aluminum oxide plus carbon forming aluminum and CO2. Let's balance this again. And now, I'm not just given one thing. I've got 270 grams of this, and I have 74 grams question is, what's the theoretical yield going to be? Well, I gotta figure out which one of these is going to run out first. Alright, so how are we gonna do this? Determine the number of moles of aluminum each will produce. Okay, pick a product. Don't say, oh, I'm gonna see how many moles of aluminum I can get from this and how many moles of CO2 I can get from that. Don't do that. Pick a product and then figure out how many moles of aluminum you can get from 270 grams of aluminum oxide, how many moles of aluminum you can get from 74 grams of carbon. You say, well, there's no aluminum in there. Well, it's reacting with that to produce the aluminum. Okay? So we're going to do both of those. So 270 grams of aluminum oxide. We're going to go from grams of aluminum oxide, the moles of aluminum oxide, the moles of aluminum. I'm going to stop right there. I'll stop at moles of aluminum. So I got 1 mole of aluminum oxide per 101.93 grams. And it is 4 moles of aluminum per 2 moles of aluminum oxide. Okay, what's that number? This is going to be moles of aluminum. How many moles of aluminum is that going to be?
3.34.
Okay. Someone else have that number? What do you have?
I got 5.2.
5.29. Is that it? Rounded off to 3, 5.29?
Yeah, you're
Okay, 5.29. Okay, now, let's go down here. 74 grams of carbon. I'm going to convert that into moles of carbon. 1 mole of carbon, 12.01 grams of carbon. Now I want to convert that into moles of aluminum. 4 moles of aluminum per 3 moles of carbon. And what's that going to be? That's going to be moles of aluminum. Grams of carbon cross out, moles of carbon cross out, moles of aluminum. What? 8.2. I hear a second. 8.2. 8.20. 8.21. 8.21 moles of aluminum. Okay, now look at those two numbers. Which is going to limit? Which one's going to be the limiting one?
Got the smaller number on.
Okay, the one that produces the least amount of aluminum. What is this saying right here? This is saying this 270 grams of aluminum oxide, when you reach this amount of aluminum, 5.29 moles of aluminum, you're going to run out of aluminum oxide. That's the most it can make. Yes, the carbon can make 8.21 moles of aluminum, but there isn't enough aluminum oxide to carry the reaction that far. You follow me? So your limiting reagent, the one that produces the least, this is the limiting reagent. I'm not going to call aluminum the limiting reagent. It is the reactant that runs out first. Is your limiting reagent or limiting reactant. So now, if you asked what the theoretical yield is, all you have to do is convert that 5.29 moles of aluminum into grams of aluminum. And you got your theoretical yield. Okay? That's going to be your theoretical yield. What happens to the rest of the carbon? It's left over. It's the 6 slices of bread that are left over at the end of making the sandwiches. You're going to get that amount of aluminum, and there's going to be some carbon left over. And that's probably how Alcoa would do it. They would run this reaction with excess carbon, and this would be your limiting reagent. You get to the end of it, heat that up, and burn the carbon off. It comes off as carbon dioxide. It just burns, disappears, and you just have aluminum. Okay, so that's your limiting reagent. Yeah.
Is there a reason why you picked aluminum, or could you do the same thing with the CO2?
Yeah. You could have done the same thing with the CO2. Just what I've seen some students do sometimes, and they end up with, they can't draw a conclusion. They take one of the reagents and they say, okay, how many moles of aluminum can I make out of that reagent? They take the other one and they say, how many moles of the other thing can I make out of that thing? And you end up with numbers, but you still can't figure out which one's the limiting reagent. You got to compare them to the same thing. But yeah, you could pick either one. Just pick one. Pick one. Take them all over to the same thing. How many moles of one of the products will it make? And the least number will be your limiting reagent. We did this with CO2, we'd come up with the same conclusion. But if they're asking you calculate the theoretical yield of aluminum, then you might as well pick aluminum. Right? Because in this particular case, we don't care about the CO2. We want to know how much aluminum we're making. Okay? All right, let's see. I'm going to just look down through this Group 4 packet. Problem 35 is a theoretical yield. Actually, it's a percent yield calculation. You got 32.5 grams of N2H4. It's reacted with excess hydrogen peroxide, and you produce 10.4 grams of nitrogen. So you're going to have to calculate the theoretical yield, and then based on that actual yield, calculate the percent yield. All right, problem 36. You're given a certain number of grams of sodium chloride and a certain number of grams of silver nitrate. So that right there is looking like a limiting reagent problem. It's begging the question, which one of these, the sodium chloride or the silver nitrate, is going to limit how much product can be produced? So in that particular case, pick one of the products, let's say silver chloride, and see how many moles of each one of that would produce. That's this kind of a problem. It's a limiting reagent problem. Problem 36. Yeah, 37 is got about everything. You've got the equation, and you're supposed to balance it. You're supposed to write out an equation and balance it. Determine the theoretical yield, and then in part C, you're given an actual yield and asked to calculate a percent yield. $38. What is that? Is that a? Yeah, that's a theoretical and a percent yield calculation. Oh, I see. There's one other concept we haven't gotten to, and that's titration. Uh-oh, okay. I'll tell you what I'm going to do. I think I'm going to give this as extra credit. This is 5 points. Don't do this now, but you can do this and turn this in with your packet 4, and I may just add, if you do this, I'll add 5 points to that packet 4 score, and it'll be extra credit points. Let's just take a peek at this, and then we'll put it away, and I need to explain titration in the last 15 minutes here. And then you'll have everything. On Tuesday, we'll be able to go on to chapter 5, the next chapter. What's the next chapter?
The packet due Tuesday?
Pardon me?
Packet due Tuesday?
Yeah, they'll be due Tuesday. Okay, take a look at this. 5 problems here, but number 1 is just begging the question: how much oxygen is needed to react with 44.5 grams of that's hexane? Number 2, how many grams of hydrogen would be produced if 33.7 grams of magnesium reacted? Assume that the other reactant, like the sulfuric acid, there's excess. There's plenty of it. Number 3, you're actually got a product. You want to make 48.7 grams of sodium sulfate. How much sodium hydroxide? What's the theoretical amount of sodium hydroxide you need to make 48.7 grams of sodium sulfate? 4 and 5 are limiting reagent problems. So you're given iron 3 oxide and hydrogen. The weight of each of those, you got to determine how many moles of iron that's going to produce. Number 5, you're given a weight of aluminum, a weight of HCl. Which one is your limiting reagent? So there's 2 more limiting reagent problems right there. This, like I said, this is stoichiometry, theoretical yields kind of calculations, and then these are limiting reagent calculations. So this brings it all together. The limiting reagent problem brings everything together. And there's more examples in here. If you want to go back through, there's some more examples to trace out.
Do you have any of the answers to those examples?
That are in here, I don't know. I will publish the answers to, I can publish the answers to that eventually. No, I don't think, some of them do work it out, don't they? No? Yeah, I thought they would have some in here.
Just don't really know if you get the right answer.
Okay. Seems like I saw that slide before. Yeah, I probably don't have them, and I don't know if I can commit to solving them, but maybe I can solve a couple. Okay, let's talk about titration. We introduced acids and bases. We talked about, an acid will neutralize a base. And if we had something simple, I have to write on the board. If we had something simple like HCl reacting with sodium hydroxide, that's a monoprotic acid reacting with a base with only one hydroxide on it. about titration right now, we're going to talk about it in terms of an acid-base titration. There are other kinds of titrations. You can do an oxidation reduction titration. Acid-base titration is a very common one. But in this, you have that 1 mole of HCl will react with 1 mole of sodium hydroxide. So 1 mole of HCl will neutralize 1 mole of sodium hydroxide. That's the way they will react. They're reacting in a 1-to-1 ratio. So it will take this amount of acid to neutralize that amount of base. Or vice versa. It will take that amount of base to neutralize that amount of acid. Okay, now, you got to start drawing on the things you've learned and pull them together and utilize them at the same time. We talked about molarity. What is molarity? Moles per liter of solution. And a titration is being done in solution. Your acid and your base are dissolved in water. So you're not taking solid sodium hydroxide and bubbling HCl gas through it. We've got an aqueous HCl solution, an aqueous sodium hydroxide solution of some concentration. What concentration? Well, in one case we will know the concentration, and in another case we won't. And that's what we're doing in the titration. We're trying to determine the concentration of one of these reactants, whether it be the acid or the base. You could conduct this either way. Well, already you know that 1 mole of this will react with 1 mole of that. You know molarity, moles per liter. You know that you can take molarity times volume, and that equals moles. You take the molarity of a solution times the volume of the solution, you get moles, particularly if this is in liters. Because what you're doing is you're taking moles per liter times liters, that gives you moles. I should have brought, there might be a picture. Yeah, there you go. I said I should have brought a burette over here, but this little diagram here, there's your Erlenmeyer flask, here's your burette. In this particular case, we're putting the base in the burette, and we're trying to figure out what the concentration of the acid is. This is what it looks like in real life. The burette, I don't know if you can see that, it has a valve at the bottom, Teflon valve, so you can turn it and you can drip in your standard solution that's in the burette into your acid. And you're dripping it in there until it gets neutralized. How do you know when it's neutralized? Well, if you added phenolphthalein, that's just one of a whole range of acid-base indicators you could use. But if you put phenolphthalein into your acid here, and it would be colorless. So it would look like water. It would be clear and colorless, as long as that solution remained acidic. But as you're dripping your base in here, you can see, can you turn the, Berko, can you turn the slide on? Yeah, you can see this kind of purplish pink color appearing, and then if you swirl this around, it'll disappear. Why? Because the base came in and made the region kind of basic temporarily. The acid reacted with it, it went back to this color. But you eventually, with 1 drop of base, you get to a point where the color appears and prolongs. It lingers, which is telling you what? You're now no longer acidic. This flask is no longer acidic. And you don't want, you stop there. That's the end point of your titration. You have to stop right there. Don't go past that. Why? Well, that's a real critically important point. That's the end point. And what does that mean? That means that the moles of base that you dripped into the flask is equal to the moles of acid that were there to begin with. That's the end point. That's the neutralization point. The moles of acid equals the moles of base. The end point, or we also call the equivalence point. This is why right here, equivalence point. That's where the moles of acid is equivalent to the moles of base. What's the moles of acid? The molarity of the acid times the volume of the acid is the moles of the acid. And what's this? The molarity of the base times the volume of the base is the moles of base. So this titration experiment, this analytical technique, it's really not an experiment, it's a quantitative technique for determining the concentration of a solution. You usually know what it is, you usually know what the acid is, but you don't know its concentration. So you have 4 variables. So how do you do this? You need to know 3 of these. Let's say that our HCl was our solution of unknown concentration. We want to determine its concentration. So we would put an exact amount of that solution. We would pipette 10 milliliters of it into the Erlenmeyer flask. We would standardize. This would be the standard sodium hydroxide solution. We would, by some method, we would prove, or we would determine the exact concentration of our base. Let's say it was 0.1397 molar sodium hydroxide. And we have it in a burette. What is a burette? A burette is calibrated. You can't see it here. You can kind of start seeing it. This is let's say that's a 50 milliliter burette. Starts out at 50 milliliters. Or it starts out at 0. At the top would be 0, and you titrate down, and at the end point you stop and you read your burette. So if your initial reading was right at the top of the burette, and you get to the point where the color lingers, you're at the end point, you find out that you have delivered 21.50 milliliters of that base into the flask. You got your end point. So what do we have here? We got this equation. This is our unknown. So the molarity of the acid is equal to the molarity of the base times the volume of the base divided by the volume of the acid, 0.1397 molar sodium hydroxide times the volume, 21.50 milliliters, and you pipetted 10 milliliters of acid into there. All right, so titration, this is a quantitative technique. You're getting a very accurate answer to your question. 0.1397 times 21.5. That's a good question. 0.1397 times
Now, because the
21.5.
milliliters are gonna cancel out anyway.
Yes. Divided by 10.
Yeah, if you're looking for volume, you might have to convert it, but when you put your base over your acid, the volumes, those little milliliters on each of them are gonna cancel out, and you're just gonna be left with a molar.
Yeah, let's convert that to liters. We'd have 0.1397 times liters. That is moles of base. But if we converted this to liters, all right, we've just divided each number by 1,000. So we would have had a factor of 1,000 here. We would have a factor of 1,000 here. And those would cancel each other out. So yes, theoretically, I am saying molarity times volume in liters is moles. What we would have here is millimoles. Yeah. Because these are canceling out, you don't have to convert them in this particular case. Just keep in mind that if you ever want to know moles specifically, that does have to be in liters.
That's also something to keep an eye on, so if one measurement is in liters and the other one is in milliliters, then you're gonna have to convert one to
Right.
the other, same thing.
All right, so that would be the answer to your question, or this question here. It would say that HCl solution was 0.3004 molar hydrochloric acid. Let me just see if that gets you there. All right, problem 41 is pretty straightforward. It is HCl with KOH or sodium hydroxide. So there's two of them there, right there. Problem 42. All right, 42, you're going to have to kind of work through that. Notice there on 42, you have a solution of sulfuric acid, 0.324 molar sulfuric acid. You are reacting that with solid sodium carbonate. So your sodium carbonate moles are going to be, in terms of molar mass, you're going to convert your grams of sodium carbonate into moles of sodium carbonate by molar mass. There's where you're going to need to multiply your molarity of your sulfuric acid times liters. Yeah, what volume? When you're talking about moles of sulfuric acid, moles of sodium carbonate, you're getting at them two different ways. You have a solution of sulfuric acid, you have solid sodium carbonate crystals. 44 is just like what we just talked about, 44A and B. 45. Oh, I got there, we did this in class. We didn't do this. Okay, the sticky wicket about problem 45 is you have, what do you have there? Oh, you got sulfuric acid, which is diprotic, reacting with sodium hydroxide. Right, the balanced molecular equation for this, assume that 15 milliliters of sulfuric acid solution is nitrated with 22.5 milliliters of 0.1200 molar sodium hydroxide. What is the molarity of this sulfuric acid? Yeah, you're going to need a factor of 2 in there. You can't just go directly the way we're going there, because the sulfuric acid has 2 protons, and the sodium hydroxide has only 1 won't do this whole problem, but let me just set it up, and then we'll be dismissed. And I'm looking at 45B. Berko, you can turn the light back on. So what do we have here? We do have here in this case, the moles of acid is going to equal the moles of base. All right? We didn't talk about it in these terms over here because there was one of these for one of these. So 1 mole of that did give you 1 mole of that. And 1 mole of this gave you 1 mole of this. Okay, you follow me? This is a monoprotic acid reacting with sodium hydroxide. And this is what is the net reaction. H plus is reacting with that to form water. We saw that earlier today. That's your net reaction. Well, on 45, we have this situation. We have sulfuric acid reacting with sodium hydroxide. 1 mole of this gives you 2 moles of this. Okay? So there needs to be a factor of 2 enter into your calculation. So we're saying assume that this is your unknown. You want to know your molarity of your sulfuric acid. And your volume of your sulfuric acid is 15 milliliters. The molarity of your base is given. And the volume of your base is given. So really what you have here, the molarity of your H2SO4 you're going to have, and we could, we might be able to leave it as milliliters, but you get 2 hydrogens for every 1 H2SO4 times your volume of your acid. This is your moles of H plus. Whereas over here, your molarity of your base times your volume of your base is your moles of OH minus. You see, you've got to get a factor of 2 into this calculation. So to isolate the moles of sulfuric acid all by itself, you're gonna have the moles of your H2SO4 is going to equal the molarity of your base times your volume of your base divided by the volume of your acid. And you're going to have to, see, you're going to divide this by the volume of the acid, you're going to have to divide this by 2. You have to factor a 2 in here to get back to what the molarity of that H2SO4 actually was. All right? So you can't just do it straight like that with a monoprotic acid reacting with a single hydroxide base. You got to get a factor of 2 because there's 2 protons for every 1 H2SO4. Okay, I think that helps you. that's the volume of the acid. Yeah. Yeah, so that's gonna be that. All right. Chapter 4 packet will be due on Tuesday, and there might be another problem in there. The one underneath it, oxalic acid, may also be diprotic. And then we'll dive into the next chapter, and what is the next chapter? It's the gas laws, right? I think it's the gas laws. So be ready for that when you come Tuesday. Yeah, chapter 9, gas laws. And if I can, I'm going to try to cover that whole chapter on Tuesday. And then maybe even the thermochemistry on Thursday. So obviously exam 2 won't be next Thursday. All right, so I'll need to get you the chapter 5 packet, chapter 9 packet, the thermochemistry.